Hello and welcome back to Zig's Math Lessons. Finishing up our introduction to calculus. 1.6, continuity. A continuous function, by definition. A function is continuous at a point where x equals a if the following two conditions are met when x equals a. F of a is defined. In other words, a is part of the domain. And the limit as x approaches a of f of x is equal to this f of a. And so this implies that the two-sided limit at a exists. So the limit from the left is equal to the limit from the right. A function is a continuous function if it is continuous at all the x in its domain. Three types of discontinuities. Well, if you can draw the function using your pencil without lifting your pencil from the paper, then it's a continuous function. However, in the second case here, we see that you can't draw this function without lifting your pencil from the paper. You draw it up to here, then you have to lift your pencil. So there's a discontinuity, and we just got a name for it. It's called a jump discontinuity. There's a couple of discontinuities in this graph. There's a hole in this graph. That's a point discontinuity. And there's an asymptote in this graph. And that's a break in the graph, and so that's a discontinuity. So we have a point discontinuity and infinite discontinuity. Let's analyze this function for continuity. What's happening at x equals minus 3? Well, there's minus 3 along the x-axis, and we can see that we could draw right through there without lifting our pencil from the page. So therefore, it's continuous at x equals minus 3. At x equals minus 2, there's a hole. And so that's a point discontinuity. At x equals minus 1, there's a jump. So that's a jump discontinuity. At x equals 0, a point has been displaced. So that's a point discontinuity. At x equals 1, well, there's a jump. So it's coming along here, and then it jumps, and a point has been displaced. So this is both a point and a jump discontinuity. And at x equals 3, there's an asymptote here. And so that would be an infinite discontinuity. Analyze the piecewise function for continuity. And this is called a piecewise function because the domain is broken up into pieces. X is defined over the real numbers. We can tell because x can go from negative infinity up to minus 1, and then it's immediately picked up by the next piece and goes from minus 1 to 1, and then it's immediately picked up by the next piece and goes from 1 on to infinity. So x is defined over the real numbers. Consider the y values at the boundaries of the pieces. Because we can tell that a line is continuous and a parabola is continuous and another line is continuous. So what interests us is what happens at the boundaries of the pieces. So we're interested to sub in minus 1 to both here and here, the first and second piece, and see if they meet. And we can see that if we subbed in minus 1 here, we get minus 2 plus 3, which is 1. And if we subbed in minus 1 to the second piece, we get negative 1 squared, which is also 1. So these two pieces meet. Now, where these two pieces meet at the boundary is at the number positive 1. So if I subbed in 1 to this piece, I'd get 1. But if I subbed in 1 to this piece, I'd get negative 2 plus 1, which is negative 1. So the second piece and the third piece don't meet. So there's a jump discontinuity when x equals 1. And we can write this down as follows. It's continuous at x equals minus 1 because when I subbed in minus 1 here, I got the same as when I subbed in minus 1 here. I got the number 1. There's a jump discontinuity at 1 because when I subbed in 1 to the second piece, I got 1, and when I subbed in 1 to the third piece, I got minus 1. So there's a jump discontinuity at x equals 1. A typical question that you might be asked is find the value of c so that the piecewise function is continuous. For this piecewise function to be continuous, the y values at the boundaries must equal when we're at the boundary. So the y values of the pieces must be the same at the boundaries of the pieces. So what we do is we equate both the pieces of the function when x equals the number at the boundary. In this case, that's 2. Plugging in 2 for x, doing the simple math, and we have it. I'm not Ziggleby Biestuk, but thanks for watching. If you liked it, leave a like. If you like the content, please subscribe. Asking questions in the comment section might be productive.